Dear students, you are welcome in this class. Today is 1st April 2023. Time is 5 p.m. And we continue with the same topic, response curve fitting. I will just show you the slides that you have seen many times. And I am a bit slow in teaching this subject to you so that you get more and more clarity. And if you remember type of equations, polynomial equations, and response curve fitting by method of least square, and you know we need to find out value of A and B. If that is done, that means this equation will result in least sum of squares, or this will be the best fit. So we try to understand this, that sum of square of differences of distances should be the least. You could follow all these, I think. Next is residual. Residual is your error, which you can see here also. The line is passing through particular point, but it is having some distance from certain points. So these distances, if you take the distance and square it, so these are errors or residual sum of square. So then you could see the correlation analysis. You also know the formula of correlation analysis, regression analysis, dependent and independent variable, some scatter plot. What is scatter plot? You have seen. And linear correlation coefficient or Pearson correlation coefficient. And you also know the simple and multiple correlation and regression analysis. So in this case, simple means you have only two variables, one independent and one dependent. Then it is simple correlation or simple regression analysis. And you will also see correlation coefficient. Correlation coefficient is many times written with capital R, and sometimes it is written with small r. Similarly, you also have coefficient of determination. Many of you may not be knowing the difference in correlation coefficient and coefficient of determination. And normally we write R for correlation coefficient and R square for coefficient of determination. Anybody has any idea about difference in correlation coefficient and coefficient of determination? Anyone has idea? No idea. So today you will see the difference in correlation coefficient and coefficient of determination. So it is simply a square. Coefficient of determination is simply a square of the correlation coefficient. And it can be represented by small r or capital R. Anybody has idea that for writing correlation coefficient, should we write a small r or should we write capital R? Similarly, for coefficient of determination, should we write small r square or capital R square? Which one is correct or both are correct?
Sir, it is small r.
Okay. So actually, it does not make any difference whether you represent it by small r or capital R. But statisticians consider that if you have simple correlation analysis, simple correlation means two variables, then use small r, or if you have multiple correlation analysis or multiple regression analysis, in that case, you can use capital R for correlation coefficient and capital R square for coefficient of determination. Otherwise, it is not binding. One can use either of these two. So there is no difference in small r square or capital R square. You can write any one of these. Now, I think I have already discussed about the coefficient of correlation. It tells the strength between two variables. Higher the value of the correlation coefficient, more is the strength between two variables. And there may be negative correlation also, where you can have values in minus. So minus value does not mean it is in minus. Actually, minus suggests the change, the nature of change. It is just nature of change. So minus or negative correlation, this negative, suppose it is negative or minus 0.998. So it is not that the value is in minus. This 0.998 is not in minus actually. This minus sign indicates a negative correlation. A negative correlation. That is the difference. So don't, these are to be considered as absolute values. Minus or plus sign before correlation coefficient is just the direction of change. Direction of change, whether it is positive change or one variable increases, other decreases. So now I think I have already discussed positive correlation, negative correlation, and non-linear if you don't have linear. And then we have seen the regression analysis, how it is done, regression coefficient, and your B is the slope of line or regression coefficient. We also discussed linear relationship with the changes in the units of the independent variable. There is constant change in the dependent variable. That is your linear relationship, can be represented by y is equal to a plus bx. So it is for the simplicity that your y is equal to a plus bx. Otherwise, if you go to IASRE statistician, they will also write one more term, plus error. So plus error is just missing here, just to make it simple. Otherwise, you should always consider that error is always added here. A plus bx plus error. And it can be multiple linear relationship where you can have many variables, x1, x2, x3, xk. Then you have seen the regression analysis by method of least square, and you know field experiments are conducted, and then you get the data, you see the significance, and do the analysis in this way. This is your input is your x, output is your y, and expected is your y0. This is from the line, and then sum of differences, and then sum of square. I think I have explained it to you. And then you can calculate the value of means from this table. If you want to calculate the value of A and B, so value of A and B is required to be calculated for fitting the equation. Then you need to take the mean of x. So summation x upon n. Similarly, mean of y, the dependent variable, summation y upon n. I think each one of you can work out the mean values from this table. If you are given numerical values, you can work out the mean of y, mean of x. So, and then you need to calculate the corrected sum of squares for independent variables, that is x. So xi minus x bar, you see it is xi minus x bar, deviation against the mean for input or for independent variable, xi minus x bar whole square. Similarly, corrected sum of square for dependent variable, yi minus y bar whole square. And then corrected sum of cross products. So you get xi minus x bar, yi minus y bar. Multiply these and take the total. So this is your corrected sum of square of cross products. So why we are doing it? We are doing it to calculate or to find out the value of A and B. These parameters which have been calculated will help us to find out the value of A and B. So value of B can be found out easily by summation xy upon summation x square. So you can find out the slope of the line. So you know how you get the summation xy. This is your summation xy, this one. And this is your summation x square. Summation y square, I will show you, it will be used later when we go for testing the linearity of the equation. So here you can easily calculate the B. And similarly, A can be calculated by the difference of mean y minus bx bar, or y bar minus bx bar. You know the mean of y is available with us, minus b. You have just found out the value of b. So you can put this value of b here and then multiply it by x bar or x mean. So now you get the value of A and B. Put it in the equation. You get equation y is equal to A plus bx. Now you are settled with the equation. You have found out it, you have fitted it, or you have fitted the response curve. Or now your job is to test whether it is a genuinely a linear equation, whether it is linear or not. Is it having linearity or not? So that is to be tested, and F test is used to see the linearity of the estimated equation, or whether the regression is significant. In other words, you can say whether the regression is significant or whether the B, the regression coefficient, is significant. It can be expressed in many ways. Overall, you want to see the linearity of the equation, whether this equation is statistically linear or not. So for doing this, we need to employ F test, and this F test will partition the variation into two components. One is variation due to residual or error, and other is variation due to regression or variation due to linearity. So there are only two sources of variation. One is regression and other is residual. And if you total them, that will be your total variation. So now you can see this ANOVA table. This is also ANOVA table, analysis of variance, where sources of variation are in first column. First source of variation is regression, or you can simply write it linear also, linear or linearity or regression. Regression and degree of freedom is always 1. As I told you, for linear relationship, degree of freedom is 1. For quadratic, it is 2. For cubic, it is 3. And then total degrees of freedom is n minus 1. So here n is number of pairs of observations. So how many pairs of observations you have? Suppose here you have 1, 2, 3, 4, 5. 5 pairs, n0, y0, n1, y1, n2, y2. So here you have 5 pairs. And you can also have 4 pairs also. So any number of pairs you can have. And then suppose there were 5 pairs, then 5 minus 1. So it will be 4. It will be 4. And this can be worked out by relationship n minus 2. N minus 2. Because n minus 1 minus 1. So it is residual or error degree of freedom can be calculated by subtracting regression degree of freedom, that is 1, from the total degrees of freedom, n minus 1. So n minus 1 minus 1. So residual degree of freedom is n minus 2. Now, sum of square for regression, that is your summation y square L, or you can say summation y square R, sum of square due to linearity or sum of square due to regression. So it is summation xy square, whole square of summation xy divided by summation x square. So this is for calculating sum of square for regression. And then you know total sum of square. See the bottom row. Total sum of square is summation y square. Summation y square. You see summation y square, where from this summation y square is coming this. I will show you later. It is just you take the deviation against the mean for y, dependent variable, and square those values and make the total. That is your summation y square. Suppose here, sum of difference y0 minus y0, y1 minus y1, you will get, and then if you square these values and make the total, that will be your total sum of square for dependent variable. So this total sum of square, I will again show you later. Total sum of square. Now you need to calculate sum of square for residuals. For residuals, this is total sum of square minus regression sum of square. This is your total sum of square. This is regression sum of square. So subtract the regression sum of square or sum of square due to regression from the total sum of square. So total sum of square is summation y square minus sum of square due to regression. Just see above. This formula is deducted from the total sum of square. Then you get residual sum of square. As a rule, general rule, now you need to calculate mean square variance, which is sum of square divided by degree of freedom. So whatever value of sum of square due to regression you will get, or linearity, divided by 1, so you will get some mean square due to regression. Mean square due to regression. Similarly, here also, you divide the value of sum of square by n minus 2, that is degrees of freedom, you will get mean square due to residual. Mean square due to residual or error mean square. Okay, is it clear? Is it clear to all of you, or you have any doubt here? Hello?
Clear, sir.
Clear?
Clear, sir.
Okay. Now, you see, you need to calculate the value of f. Value of f is mean square due to regression divided by mean square due to error or residual. Mean square due to linearity divided by mean square due to residual or error. Means this value should be divided by this value. Then you get f calculated. So f calculated value you have, and for f test you have f table also. In f table you have level of significance, say 1% or 5%, whatever you want, you can choose the level of significance from the f table. I think most of you must have seen T table, F table, R table, and many kind of tables are there in statistics. So in F table, you need to see the value of F in the table, or table value of F at 1% or 5% level of significance, and 1 and n minus 2 degrees of freedom. 1 and n minus 2 degrees of freedom. You know, in F table, you will find 2 degrees of freedom. One is read horizontally and other is read vertically. Remember, one is read horizontally, other is read vertically. You read it horizontally, then vertically. Suppose 1. So 1, you need to go to the horizontal side on the table, and n minus 2 on the vertical side. And at the prescribed level of significance, you find out the table value of f. And then if your f calculated is greater than table value, then your test is significant, which means that your equation is genuinely or statistically linear. The results are significant, means your equation is linear. It does not have any other kind of relationship. It has only linear kind of relationship. If test is turned out to be non-significant, that means your table value is higher than the f calculated value. Then results are non-significant. That means it is not a linear equation. It is not a linear equation, or it may have some other kind of non-linear relationship. So those will be your conclusions. So here you can see just mean square due to regression, sum of square, just what you have seen in the table. Sum of square due to regression or linearity divided by degree of freedom. Then mean square due to residuals is equal to sum of square due to residual divided by degree of freedom. And then f calculated, mean square due to regression or linearity divided by mean square due to residual or error. So you can see in the last table, I have shown you how to calculate mean squares. This column you have calculated. And f calculated, mean square due to regression divided by mean square due to error or residual. Now what will be your inference? Compare the calculated value of the tabular value at 1 and n minus 2 degree of freedom. 1 and n minus 2 degree of freedom. If it is t-test, in t-test you have only 1 degree of freedom. Means you don't have to see horizontally and vertically. You have one-way degree of freedom. So compare the calculated value of f to the tabular value at 1 and n minus 2 degree of freedom. The linear relationship is just to be significantly different if the value of f calculated is greater than table value at the prescribed level of significance, 5%, 1%, and so on. Otherwise, we look for higher degree of regression. So you normally take in agricultural sciences, we normally take 5% level of significance. Can anybody explain me what is level of significance? Alpha, it is written by letter alpha. It is represented. What is it? Level of significance.
So it is the extent up to which we can take risk. After that, we have to reject the hypothesis.
Good. Any other? It is good. Any other participant, student, wish to say something more about level of significance? So actually in statistics, it is very simply defined, but we don't know what does it mean. Do you know about type 1 error and type 2 errors in hypothesis? Anybody know about type 1 error, type 2 error, or you know about null hypothesis? Hypothesis of no difference is null hypothesis, means two or more means are equal. It is assumed. That is null hypothesis. And alternate hypothesis means are not equal. That is okay. And then sometimes you will see there this type 1 error and type 2 error related to hypothesis. Anybody knows about type 1 error and type 2 error? And so I just forgot, but it is something like this that if
Sir,
I
So when the hypothesis is true and we are rejecting it, it is type 1 error.
correct, yes,
And in type 2 error, if it is wrong and we still are accepting it, that is type 2 error,
very good,
which is more serious form of error.
excellent, very good. So this level of significance is also defined based upon this type of error, this uh, probability of committing type 1 error is called as level of significance. So this is very complicated definition given by a statistician. Then we should know what is type 1 error. So it is not very clear definition. Probability of committing type 1 error is called as level of significance. हमने रट लिया था जब पढ़ाया गया था लेकिन मतलब नहीं समझे. We could not follow the meaning. Does anybody knows the meaning of this? Level of significance, suppose 1%, 5%.
So I think in 5%, it means that in any hypothesis, 95% of the time it will be true. So we will accept it.
Very good.
Something like
Confidence.
that.
Confidence interval. Very good. So, dear student, you get more clarity and it is on your fingertips. You can learn yourself what is this level of significance. This is very, very important. Simple terminology in statistics, you should know what is variance, what is standard deviation, mean deviation, or measures of dispersion, and mean, median, mode. These should be always on your tips. So anyway, now this part is over. I go to the next part. Wait a moment, I'm just opening a new file. Just a minute. I'm just opening another file. So can you see the slide, dear students? Can you see? Hello?
Yes, sir.
Okay. Now I will explain you the what you have seen right now, how to calculate the value of A and B, how actually fit the equation, how to practically find out the value. I am showing you manual method, and what I am showing you now, it can be done on computer also. Within seconds you can do it, but it is better to understand background or theory or statistical theory behind it. So suppose this is an example through which you will learn the fitting of the regression equation or linear equation. A field experiment was conducted by taking different levels of nitrogen in mustard. That means it is independent variable, different levels to test its effect on seed yield. Seed yield would be the dependent variable. From the data given in table 5, fit a linear response equation. Fit a linear response equation and test it for linearity. Means you need to test the linearity of the equation. Also plot the response curve manually. Also plot means make the line, regression line, response curve from the computed equation and perform the correlation analysis. So you have to do many things. First, you need to fit the equation, then test it for linearity, and then plot it, make it in the form of a regression line or this straight line, and then go for correlation analysis also. So these are your jobs. Now you can see it is very, very simple, very, very easy. So in first column, you see it is X, kilogram nitrogen per hectare, 0, 40, 80, 120. You can see it is equal interval, but you can also have unequal intervals. Unequal intervals you can have. There is no issue. And then yield. Yield is your dependent variable, quintals per hectare. That is in capital Y. Now this quintal per hectare is not used. This is obsolete unit. And now these days we always use tons per hectare or kilograms per hectare. But this quintal per hectare I'm using just to mark respect to our teacher, Dr. R.R. Patil. This example was given by our teacher right in the agronomy division long back. So it does not matter whether unit is quintal or tons per hectare here. You are just learning to fit equation. 17.20, 18.50. So you see these data or observations are in pair. If you have 0 nitrogen, you have 17.2 quintals per hectare of the yield. So this is your N0, this is your Y0. 40, N1, you can consider it N1 and then Y1, N2, Y2, N3, Y3, something like that. So here you can see there are 4 pairs. 1, 2, 3, 4 pairs of X and Y. Now you need to take the deviation against the mean. For this, you can take the mean. Take the mean of X bar you need to calculate. So how much will be the mean here? 0, 40, 80, 120. Anybody? What would be the mean here?
So mean
60.
60.
Good. No, 60. It is 60. The mean is 60. And in the next column, Y mean is 19. You need not to do it, I tell you. So mean here is 19. If you take the mean, 19. So now you take deviation against my mean for X, Xi minus X bar. So here I means ith pair. First pair, second pair, third pair, fourth pair. And X bar is your mean. So from 0 minus 60, you get minus 60, 40 minus 60, minus 20, 80 minus 60 plus 20, 120 minus 60 plus 60. So you can see the total of all these values is 0 because it is deviation against the mean. Similarly, Y, small y, you see it is deviation against the mean of dependent variable. Yi minus Y bar. So value of Y bar is actually 19. So 17.2 minus 19, you get minus 1.8. 18.5 minus 19, you get minus 0.5. 19.8 minus 19, you get 0.8. 20.5 minus 19, you get 1.5. Again, you make the total of this, it will be 0. Now in the next column, you see this deviations against the mean are squared here. So squared here, 3600, 400, 400, 3600, and you can take the total. Total becomes 8000. So this will be your summation x square. Summation small x square. So that will be your corrected sum of square for independent variable x. Then corrected sum of square for cross products. You have small x here, deviation. You have small y here, deviation. So multiply these two columns. You can multiply these two columns to get xy. So minus 60 into minus 1.8, you get 108. Minus 20 into minus 0.5, you get 10. Plus 20 into 0.8, you get 16. And plus 60 into 1.5, you get 90. If you make the total of all these, you get 224. 224 is summation xy. Summation xy, small xy. Next, small y square. So you get one column here, small y, the deviation against the mean. The values are there. If you square these values, then you get y square. So minus 1.8 into minus 1.8, you get 3.24. Minus 0.5 into minus 0.5, you get 0.25. And then you get other values also. So you get the total. Total of y square becomes 6.38. So this is 6.38 is your summation y square. Summation is small y square. So now from all these values, we will calculate the value of a and b and also test the equation for linearity. Anybody has any doubt in this? These calculation, anybody has any doubt? No doubt. Your silence tells that either you are not present or you have no doubt. Anyway.
No doubt, sir.
Okay, now you see how we can do it. Mean of x, summation x is 240 by 4, 60. And mean of y in the last table, y bar, summation y upon n, 76 upon 4, it is 19. And you see corrected sum of square in the last table for summation x square was 8000 and for summation y square was 6.38. Remember this summation y square is also called as total sum of square. When you take deviations against the mean for dependent variable y and you square those values and take the total of all the pairs, then it becomes total sum of square, which is here 6.38. Now we go to the next, you can click the same link again, I think, and we will go there. I will end it here. So continue. Now you can see summation is small x square or x square, and this summation y square is total sum of square, which we found out 6.38. You can see this 6.38 is there. 6.38 and 8000 is summation x square and 224 is your summation xy. Now you can calculate the value of b, summation xy upon summation x square. 224, you put the value and 8000 you get 0.028 is your b, regression coefficient. That means if you make a unit change, 1 unit change in x, there is 0.028 unit change in y. Is it clear the meaning of b? If you make 1 unit change in x, then there is 0.028 unit change in y. That is the relationship. Now you can calculate the value of a, y bar minus bx bar. This is the relationship you need to remember. In your examination, I will give you one such problem that you will solve, and so you remember formula to calculate b and a and also correlation coefficient. Those will be...
Hello, sir.
Yes.
Sir, I think there is no need to calculate the a by formula. If we put the value of x is 0, that means when the input is 0, the first yield will be the value of a, that is the intercept.
Yeah. Yeah, that can be done, but as a teacher, I need to teach you this way.
Okay, sir.
Yeah. So you can calculate it. A is calculated by difference method. Y bar minus B. I got it. Y is equal to A plus BX. I appreciate. So here A is equal to Y bar minus BX bar. And you can put the value of Y bar as 19 minus value of B. Just now you have calculated 0.028. And this 60 is the mean of X. Then you get 17.32. So this is the value of A. So now you have found out the value of A and B, put it in the equation, and that is your equation. So now you can see some details about this equation. You can see it. The linear equation Y is equal to, so in place of A, you have put 17.32. In place of B, you put 0.028. So needs to be tested for linearity. Now we want to test its linearity, whether it is a linear equation, means rate of change is constant. So whether the two variables are really following a linear relationship or have some other kind of relationship. What we do here, we go for F test. I'm repeatedly saying it. The ANOVA is performed. ANOVA means analysis of variance, means the variance is partitioned into different components. So it's performed and variation partitioned into different components. That is linearity or regression and error. Error is your residual. And F test is used to test the significance. I have shown you sometimes back. Sum of squares for regression, sum of square for residual, and total sum of squares are calculated. The slope of a line regression line may be positive, negative, or zero depending on the relation between y and x. Means you can get the value of B, regression coefficient, as positive or negative, or sometimes it can be zero also. Now you see testing the significance of linear equation. Now you need to work out or to calculate different sum of squares and mean squares. So as I told you that total sum of square is summation y square. Value is 6.38. Just now you have seen in the table. Sum of square due to regression or sum of square due to linearity. Formula is summation xy whole square divided by summation x square. So you put 224 whole square and divided by 8,000, you get 6.27. This is sum of square due to regression. This is first source of variation. Second is residual. Residual can be calculated simply by difference. From total sum of square, you can deduct the sum of square due to regression. That is 6.27. So here, this sum of square due to residual is equal to summation y square minus your sum of square due to regression or summation xy whole square divided by x square. So you see this formula is here. So you can put 6.38 as the total sum of square, this 6.38 minus 224 whole square divided by 8,000. The same thing. You subtract it and you get 0.11 as the value of sum of square due to error or sum of square due to residual. Is it okay?
Yes, sir.
Now, mean square can be calculated by dividing the respective sum of square by degrees of freedom or dividing sum of squares by respective degrees of freedom. Here, mean square due to regression or linearity can be calculated if you divide sum of square due to regression or linearity by degree of freedom. 6.27 divided by 1, you get 6.27. Mean square due to error or residuals, sum of square due to residual or error divided by degree of freedom, you get 0.055. And then F calculated. Mean square due to regression divided by mean square due to residual. 6.27 divided by 0.055. This value divided by this value. Therefore, you get 114 as the F calculated value. So here I can summarize all these calculations in the form of a table. So source of variation is linear, or you can call it regression. Is 1, always 1 in linear equation, and total is 3 because you have 4 pairs of observation. 0, you must have seen there are 4 pairs of observation. 1, 2, 3, 4. So there are 4 pairs of observation. So total degree of freedom n minus 1, 4 minus 1, it is 3. And 3 minus 1 gives you 2 residuals degree of freedom. Sum of square you have calculated for regression, and this is for error or residual. This is total sum of square, mean square. All these values divide by their respective degree of freedom, 6.27 by 1, 0.11 divided by 2, and so on. 6.27 divided by 0.055, you get F calculated, and table value is 18.51 at 5% and 98.49 at 1%. So you can see this, and at 1 and 2 degree of freedom. When you see F table, so it is to be seen at 1, 2 within bracket 1, 2 bracket close, 1, 2 degrees of freedom. So what is your judgment about it? Your F calculated is 114, and F table even at 1% is 98.49. What is your take?
Sir, the equation is linear.
Exactly, correct. So on comparing the calculated value to the table value, the linear relationship is found out to be highly significant because it is significant at 1% also. That means it is highly significant. Normally, if it is significant at 5%, we say it is significant. If it is significant at 1% or higher or lower level, we can call it highly significant. Normally, we put 1 star for 5% and 2 star for 1%. I'll show you later how you put 1 star and 2 star. So now you agree that it is significant both at 5% as well as 1% level of significance. That means there is no other kind of relationship. It is having genuinely a linear relationship. So now we need to plot it. We need to plot it at a chart paper. You must be remembering your student days in 8th class or 6th class, 6th standard, when you used to calculate the coordinates. Randomly, you got one polynomial equation, and you would randomly put the value of x to get the value of y. And you used to find out 2 coordinates, x1, y1, x2, y2, x3, y3, and so on. And then you will plot all those points. You will just put those points on graph paper and join the line. And join the line, if you recall your days, you will make 4 quarters. One is on the right side, plus, plus, and then minus, plus, then minus, minus, and then plus, minus, something like that. And you used to make lines. So same way we can do it here. Using the estimated linear regression equation, y is equal to 17.32 plus 0.028x, compute the estimated y values. One corresponding to the smallest value, x minimum, and the other corresponding to the largest value. So here you have lowest level was 0 for nitrogen independent variable, that is your x, and highest level was 120. So if we estimate the value of y for 0x and 120x, then those will be used or those will be used to draw the line. You will have y0, respective y0 when you have x0, and you will have respective y120 when you have x120. So here y minimum means the minimum value of y is a plus b bracket mein x min. X min is 0. So you can see y minimum is, or y0 you can say, y minimum is 17.32 plus 0.028x. So in place of x, just in the equation, you have put the 0 because this is the lowest value of x, and you get 17.32. Similarly, Y max, maximum yield, A plus B x max. At x max, that is 120, you will have maximum yield. So Y max is equal to 17.32 plus 0.028, 120 in place of x, and then 17.32 plus 3.36. So you get 20.68. So dear students, here, this is the estimated value from the equation, that at 120, you will get 20.68. Otherwise, you can see the actual value. Here you see the actual value is 17.240 and 20.5 for 120. But you can see the difference in estimated values. These values are from the estimated equation. So it has become 17.32 in place of 17.2, and it has become 20.68 from 20. Whatsoever it was, 20.5 tha kya tha? But it has changed. So you can see, okay. So you can see that these are the estimated value and those were the original value. Here you need only two value because your line is a straight line. So you need not to calculate the estimated values for 40 or, for 40 or 80 hours. Not required because rate of change will be constant. So you need only 2 points. One is lowest or minimum point and other is highest or maximum point. So only these 2 points. So now you have x minimum is 0 and y minimum is 17.32. So these are the point 0, 17.32, and then 120 and 20.68. So these are the 4 points. You can plot them on the equation. So here you can see this is how you can plot it. You have 0 at 0, 17.32. You just put a point here, and then at 120 you have whatsoever you had, this 20.68. So here you put the point 20.68 and join these 2 points. Join these 2 points, and then you need to write the equation here on the line. This is regression line. Also, regression line, you can call it response curve also. Of course, it is not looking curve, but usually you can call it response curve. 0.28x plus 17.32 equation. And you know on x-axis you have nitrogen and y-axis you have yield, dependent variable. One more thing you are seeing here, that is R square is equal to 1. I will explain it later. But at this point of time, you can see R square is 1. That when the line is touching or passing through both the points, it is touching both the points. Line is on the point. That means it is the best fit. Whenever you have best fit, the higher value of R square are observed. Here it is 1. That means it is the best fit. No other fit can be better than this. I will explain you later. Just wait for the time. Now you see one more equation I have artificially plotted for you. So this is y is equal to 2x plus 1. Sometimes instead of writing y is equal to a plus bx, you can also write y is equal to bx plus a. It does not matter. You know it. Either you write 2x plus 1 or 1 plus 2x. The meaning will remain same. So y is equal to 2x plus 1. And here also you see r square is 1. R square is 1, means it is the best fit. And the line is passing through the points. So in such cases, you can directly join the points when your R square is 1. So now you can see at intercept is 1 here. Intercept is 1 here. So it is 1 here. You can see at 0. At 0, it is 1 here. And when you move from 0 to 1, 0 to 1, and you are here, you are moving from 1 to 3, means difference of 2. Here, the difference of 2, and here it is 1. So 2y1, it will be 2. It will be 2. The value of B or regression coefficient will be 2. You can calculate anywhere. Suppose this is 3, or this is, you can take any point, 3. You go straight, you find 7, and this is 1 is minus, so you get 6. 6 divided by 3, you get 2. So regression coefficient is 2. The change is always 2. The change is always 2. Is it clear to you? The regression coefficient. from this picture? Okay. Now, corrected. Now, just now you have seen the graphical representation of a linear regression. Now, what are the characteristics of this? Very important. The line must be drawn within the range of values of x minimum and x maximum. It is not valid to extrapolate the line outside the range. Suppose you have data from 0, 40, 80, 120. So you can have predictions, or you can have line only within the range of 0 to 120. You cannot extend the line beyond 120. Because you have not recorded the data. You have data only up to 120 level. Therefore, it is not logical to extrapolate the line or data. The line must pass through the means of both the variables x and y. This line, if it is a linear, then it must certainly pass through the mean of both. Like in this case, the mean was 60. So you just take a line 60 like this, here point will be 16, and you can go to this side. So it will be somewhere around 19. So you can see this point. So the mean of x and y, they cross each other. The line must pass through the means of both the variables x and y. The slope of the line is b, also called as linear regression coefficient. The line, if extended, must intersect the y-axis at the y value of a. You can see here it is intersecting. So this is y value of a, or value of a, you can see. If a is 0, then this line will start from the point of origin. Computation of coefficient of correlation and determination. Now you will see, you will see the coefficient of correlation now. The simple linear correlation analysis deals with the estimation and test of significance of the linear correlation coefficient, which is a measure of the degree of linear association between the two variables. Now you remember that correlation coefficient tells us the strength of relationship. The linear strength of relationship between two variables is judged by correlation coefficient. Generally, higher value means they are more closely related, and if you have lower values, you can say they are loosely related. But can we test it statistically? Can we know whether the relationship between two variables based upon correlation coefficient is significant? So in this case, like any other test, you need to test the significance of correlation coefficient. So correlation coefficient must pass some test of significance. What is that test of significance? I will show you now. So, but before that, see the important features of the correlation coefficient. What are the characteristics? Dear students, these characteristics are very, very important. And sometimes in any exam, you will find some objective question from this part in one form or the other form. So you must see the features of the correlation coefficient, that is R, small r. Value of R lies in the range of -1 to +1. Okay, these are the extremes, -1 to +1, and in between these means it can be -0.996 and it can be +0.9999, something like that, or up to +1. And extreme values indicate perfect linear association. Extreme on both sides. And mid value of 0 indicate no relationship between two variables. Now, suppose you calculate the value of correlation coefficient, and now you want to make some interpretation. You can do it. What you can do, you can square the value. Square the value of correlation coefficient, and you can know the fitness level of the data, how much it has fitted the data. For example, with an R value correlation coefficient is 0.9. The implication is that 81. So you square it to make it coefficient of determination. You square 0.9, so it will be 0.81. And this 0.81 can be multiplied by 100. So you get 81%. Now you can see that the 81% is you get by squaring, by getting the coefficient of determination, that is R square, which is 0.81, multiplied by 100 to make it in percentage, then it is 81%. So what is the meaning here is that 80% of the variation or variability in the variable y can be explained by the linear function of the variable x. So in case, suppose you get 100%, suppose your correlation coefficient is 1, then if you square it, you will get 1. So here coefficient of determination is 1 and multiply it by 100. So you get 100%, 100% variability, 100% response of y is basically because of x, Here 81% is because of x, but 19% may be due to some other sources, and that we do not know. Therefore, 19% will go to the error. 19% will go to the error or residual. The minus or plus sign attached to the R value, correlation coefficient value, indicates the direction of change in one variable related to the change in other. So minus sign only indicate the direction of the change, or also is the case of plus sign. It also indicates the direction of change. If it is minus, that means negative correlation. Plus means positive correlation. Even though the 0 R value, sometimes correlation coefficient can be 0, indicate the absence of linear relationship. If the value of R is 0, means there is no linear relationship between two variables, but it does not indicate the absence of any other relationship. In such cases, variables may have non-linear or curvilinear kind of relationship like quadratic form. Non-linear or curvilinear have same meaning. They are equivalent. The value of R continues. The value of R does not change if all values of either variable are converted to a different scale. The value, because it is absolute, it is an absolute value. So if you change the units, suppose from kg you make quintals or in tons whatsoever, but the value of correlation coefficient will not change if it is converted to different scale. The value of R is not affected by the choice of X or Y. Interchange of X and Y values and the value of R will not change because you will use the same data. If you if you put the data of Y in place of X and data of X in place of Y, it is not going to change the correlation coefficient. It will remain the same. R measures the strength of a linear association. It is not designed to measure the strength of an association that is not linear. So only means the linear relationship is measured by correlation coefficient. Other kind of relationship cannot be measured by correlation coefficient. Or if you have other kind of relationship, then you need to, or non-linear relationship, then you need to first linearize the equation. Then you can find out the correlation coefficient. Now, testing the significance of R. As I told you just a few minutes back, that we want to see whether R is significant or not. How to say that? Suppose you get value 0.8 and somebody gets 0.9. So how to say that which is a good value or which is statistically different? So for this, you need to go for a test, a statistical test. So testing the significance of correlation coefficient. Requirements. First, what are the conditions when you can test the significance? So following requirements should be satisfied when testing hypothesis or making other inferences about correlation coefficient. When you go for testing, number one, the sample of pair data is a random sample of quantitative data. First thing is that you have drawn a random sample from the population. There was no biasness. and it is quantitative data. The qualitative data cannot be used. It is always quantitative data that can be used to calculate the correlation coefficient. Here, quantitative data means numbers, data in numbers. The sample data have not been collected using some inappropriate method. Visual examination of the scatter plots must confirm that the points approximate a straight line pattern. Means you should make a scattered plot or diagram and see the trend. So trend should look like linear trend, whether it is positive, whether it is negative, but it should show linear kind of trend. Any outliers must be removed if they are known to be errors. Sometimes there can be some unexpected data of the dependent variable. Then those should be removed. Just remove them. For example, the grain yield in this case varies from, the grain yield varies from, say, just I am telling you the meaning of outlier. Here, the grain yield varies from 17.2 to, you can say, 20.5. Okay. There is 3 quintals difference, only 3 quintals difference in these data. And if I get next data, say 160 kg, and I give value of Y as 50 quintals. So at next level, if I give 50 quintal, then this can never happen. This is wrong data. This is outlier. It is telling something wrong. It is telling lie. So unusual data, which is not following the trend or which is not in general range, is normally considered as outlier. This outlier will disturb everything. You know, the example of one fish, one rotten fish can spoil all fishes, something like that. एक मछली सारे तालाब को गंदा कर देती है. So similarly, one outlier can disturb the calculation of correlation coefficient. So those outliers should be removed. See the last line. Any outlier must be removed if they are known to be errors. Now, how to test the significance? The procedure of computing the simple linear correlation coefficient is given below. So now, just to recapitulate, just to see it. Now, first, what you did, you have fitted the equation. You have found out the value of A and B. Then you have tested that equation for linearity, for significance, whether regression is significant or not. Then you have plotted it. The third step was plotting it, making a chart, making a graph or line. And then you are doing correlation analysis and coefficient of determination. I will show you. So now you see general formula of calculating the correlation coefficient. I think most of you know about it. There are different ways to write this formula, but most people write in this way. Summation xy upon under root summation x square into summation y square. So here you put the value 224 and summation x square, you have seen the value before, 8,000, and summation y square, total sum of square. So for the same example, you have calculated correlation coefficient as 0.991. Okay, this is fine, but how can I say that it is significant? How can I say this correlation coefficient is significant? To know the significance of the correlation, there are 2 different methods. One is on the left side, other is on the right side. Method 1 is, it follows the t-test. You can go simply for t-test, how to calculate the value of t. This is the formula you need to remember. T-test is used to test the significance of correlation coefficient. R is the value of correlation coefficient divided by 1 minus r square upon n minus 2. Or you can take this n minus 2 above this also on the as numerator. Under root n minus 2, you can take it upside also. So then you will calculate the value of t, calculated value of t, and you will compare it with the table value of t at the prescribed level of significance and at n minus 2 degrees of freedom. At n minus 2, n means 4 minus 2 degrees of freedom. So if your t calculated is greater than table value, so your correlation coefficient is significant. The other way is, method 2 is, use fewer calculation. So method 2 is good. It is given by Fisher. So what Fisher did, he developed some correlation coefficient tables based upon level of significance and degrees of freedom. He has developed correlation coefficient tables. So what is there? You get level of significance and degrees of freedom. You can directly see the table value of correlation coefficient and compare to the calculated value. So there you need not to go for t-test. So this Fisher uncle has been very, very helpful to students, to people. So here is the t-test. Last time I have shown you t-test. So you can calculate the value of t like this. So it is the same formula what you see behind this one. Only thing is that n-2 has been taken as numerator here. You can put the value of n is 4, r is known to you, and you can calculate the t value. And then compare at the table value of t at n-2 degree of freedom. And here the table value is 2.0739. And this calculated value is 35. That means it is significant. And this is the case done by this Fisher. The distribution of the correlation coefficient for samples from a bivariate normal. Bivariate means this paired normal population having correlation is equal to 0 has been discovered by Fisher, who linked it with the student t-test through the transformation. He used this transformation or this statistical procedure to find out the R table, correlation coefficient table. So now I am showing you the correlation coefficient table. So these are the correlation coefficient table, just very easy to understand. Suppose your R square value was 0.991. Here you use 4 pair of observations. So n-2 is 2 degrees of freedom. So at 2 degrees of freedom, and at 5% or 1% level of significance, you need to see the table value of R, correlation coefficient. So here is the correlation coefficient table value, and your degrees of freedom is 2. Degrees of freedom is 2. And here, this side is your level of significance. You want 0.5. 0.5 means 5%. Here, 0.02 means 2%, 1%, and then 0.1%, and so on. If you multiply these values by 100, you get in percentage. Suppose it is 5%. So at 5%, you have 0.950. At 0.02 or 2%, you have 0.98. At 0.01 or 1%, you have 0.91. So your value is 0.991 actually, calculated value. So therefore, that is significant even at 5%, 2%, and 1% level of significance. Hope you understand this meaning. And if correlation coefficient is significant at 5%, you can put 1 star on the correlation coefficient. If it is significant at 1%, you can put the 2 stars. So this is how it was your 0.991, and you can see the table value of R, and you can see the significance of the correlation coefficient by this method also or by t-test. So test of significance, you can see here, the table value of TR at 2 degrees of freedom is 0.95 at 5%. At 5%, 1%, one was at 1%. I think at 2 degrees of freedom, at 2 degrees of freedom, yes, 2 degrees of freedom, 5%, it is not 1. Maybe there is some problem with this. Hope you understand this. The table value is less than the calculated value. Your calculated value is 0.991. Table value is 0.95. That means your correlation coefficient is significant. Now, what is the inference? Here, R values are significant at 1% level of significant. If you consider table value as 1, assume it is 1, then it is non-significant. If it is less than 0.991, then it is significant. So in the above case, the 100 R square means your correlation coefficient was 0.991. You can square this value and you get 0.982. That means 98.2% of the variation in Y can be explained by the linear function of the variable X. Other way to write is, we conclude that 100 R square. See the other ways of interpretation of correlation coefficient. How else we can write it? We conclude that 98.2% of the variation in the seed yield of mustard can be explained by the linear association between the seed yield of mustard and the nitrogen application rate. So this is how we write the inferences about the correlation coefficient, how it can be used, how it can explain our data or our equation. You can also write this way also. This implies that about 1.8% of the total variation in seed yield of mustard can be explained by factors other than nitrogen application. Means 98.2% variability is explained by nitrogen, by the linear relationship between X and Y, but remaining cannot be represented by linear function. Or 1.8% of the total variation in seed yield of mustard remain unexplained. So last minute is left. I will continue tomorrow also. From the coefficient of determination, I can stop share. And you can rejoin. You can rejoin just for 1 minute or 2 minutes. I will take your attendance and I will answer your questions. So you join it third time also. If you have any question, any point of discussion, it is time to get clarifications. Yeah, one by one, you can ask any point. Anything which is not understood to you, it is very simple thing, I know, but there may be doubts or some clarification. I welcome those clarification. Is it clear to everyone? Hope you are studying well, and at least I can show you the PG lab of agronomy. I'm in the department and you can have a look at this lab. You could have come practically also. On this side, you can see some instruments in IRI. I can show you this. This is the lab. And on the other part, students do analysis work here. So hope you will be able to see it. Anyway, I take your attendance. You can show your faces if you like. Good. So actually, seeing each other is also important, my dear students, because next time when you come, if we meet in a train, if we meet in Delhi, so meet in IRA, at least we should be able to recognize each other. That is good to see each other also, at least in class. You can keep your videos on, no problem. So I take attendance, and if you have any question, any doubt, and just one last message is that you should read more and more. Whatever you can read, you find any paper, read it. Go on reading. And have some books, hard copies. You will surely invest some money because continuously on mobile, it will damage your eyes. If you are on even laptop or desktop, whatsoever. So you can have some hard copies also. Your friends are there. We in IRA, we have one bookshop and you can get the number. You can talk to your seniors. I'm not recommending you purchase X or Y book, but you should buy some books, hard copies, and you just put order. Mr. Sharma is very kind here in IRA, and he will post to your home. Within 5 days, 10 days, you will get all competitive books. You just make the list of books from your seniors, and then you talk to Sharma and place some order, and he will surely send you book. Or if you get any problem, if you want to buy, you make at least 8-10 books you should have now. Okay, you don't buy expensive books like Nature and Properties of Soil and so on, but local books, Kalyani publisher books or other books. I'm not recommending any publisher. I mean, the cheaper books you can buy and keep beside you. Read as many books as you can, just turn pages. So you make it habit. Few days back, I was listening that one Israeli person reads 16 books a year. 16 books a year average. And in India, it may be hardly 10-20 minutes of one person in a year reading books. So message is why these Israelis are so intelligent, so fast. Why European people, if you see any Angrez passing through the train in your trains, he will always have a book in his hand. I have seen. So what I mean, read anything, whatever you like. It will open your brain. Thank you very much. And if you have any question on this subject, you can ask. Otherwise, you can read from notes I have given you. Thank you.
Thank you,
Thank you,
sir.
sir.
Okay, bye.
Thank
Have
you.
a nice time. Have a nice time.
Thank you, sir.
Okay, dear. Okay.